Okay, so we had the theorem of the video before. So let's start proving the second one. For each f, I want to see that this integral of TSF is in the domain, and that to make a of this is TTF minus f. Let's start with that, okay? Okay, so we want to see that the integral 0t of ds f ds is in the domain, okay? And that a of this is equal to tt f minus f. Okay, so we want to see that this is in the domain, so let's see what it is. AH of square of 0t ts fds. Okay, so we know that then we can take the limit and see what happens if it is in the domain. So this is equal to th minus I over h multiplied by the integral 0t ts fds. Okay, and okay, so this t depends of h, so we can rewrite this as 1 over h 0t, well, th minus I all multiplied by ts fds. Okay, so by the semigroup property we will unite ts with th, and we will obtain the integral 0t t of s plus h f minus ts f all ds. Okay, so now this will be equal to 1 over 8 integral of, and now we will make a change of variables. We will take the 0 as h, t plus h, and we will call t of s as f ds minus 1 over h integral 0 t ts f ds. Okay, so just with an adequate change of variables we obtain this. Here we didn't make anything, we didn't change anything, so now what we're going to do, this will be equal to integral, okay, let's separate. The integral here is t plus h, okay, now it's not going to be t, it's not going to be h, it's going to be t of t is f ds minus 1 over h 0 h t s x ds. So let's make some room here. Okay, so what we did here is just changing the limits now, because in here in this part we have an integral. Suppose that h is small, we have t here and t plus h. The first one is between h and t plus h, this, and here we have subtracting an integral of the same things, and 1 over h, you can take it out, of 0t. 0t is this. So we are taking this part plus an h factor. Okay, the same we are doing here. We write it differently, but it's the same. So we have 0 h t t and t plus h. So here we had the first one was h t plus h. We subtract 0t, and here we have, so we take all these to the first one and then an h factor. Okay, and here we will have the same because we have t plus h, and we take h, what we did here, we take the h. Okay, so we are doing the same thing here, just changing the limits of the boundaries of the integrals. Okay, so now we take this and we take the limit when h goes to 0 plus. Okay, and not only we take the limits, and so also we have to apply the fundamental theorem of calculus, because we will have, for example, for this term, the limit on 1 over h of t plus h t tsf ds. So this is like taking the derivative of an integral. So this will be what we have inside tsf in t. The same will be when we take the limit when h goes to 0 plus of 1 over h, but now to 0 h of tsf ds. Now will be, instead of t, it will be 0. So this will be equal to ttf minus t0f. Okay, the 0 f is just the identity, so this is equal to ttf minus f, which is what we want to see. In particular, in here we have the result of 1. Wanted to see that THTSF is TTF. Well, here we arrived to that. Okay, so for the third one, we have to recall the theorem that we proved before, this one, number 2, that we had that TTF is equal to ATTF, TTAF. Okay, and we will use it, just integrating, we will obtain the result, because we know from 2 of that theorem that ddt TTF equals to ATTF equals to TTAF, and if we integrate this between s and t, okay, and here applying the fundamental theorem of calculus, we will obtain here TTF minus TSF. Okay, so that's what we wanted to see. Okay, so this is a theorem that is similar to one we did when we started in the scalar case. That is that a C0 semigroup is uniquely determined by its generator. Okay, and the proof is similar to the one in the scalar case. So suppose that we have T and S, okay, two semigroups, the 0 semigroups that have the same generator. Okay, the same generator A, let's say. Then let F is in the domain of A, and well, let T greater than 0. And recall how we did in the scalar case. We define, let's call it U, that go from 0t to x. And we define it by U of s equal to T of s on s t minus s f. Okay, so we have, okay, so let's take the derivative in s. Okay, so this what would be, this would be the derivative in s of let's say ts. Okay, st minus s plus ts multiplied or composed by the derivative ds big S t minus s. Okay, so recall that ts and s, t and s are semigroups. We are deriving semigroups in their own variables s. So we know we have to go back to what we did, but we know that dTTF is ATTF. Okay, so we just will apply that. So this will be equal to, let's say, TS AS T minus S, and here we can say that this is TS. Now we have a minus here, so this will be minus a s t minus s. Okay, so in both sides I forgot an f, and so here we have the same things but with the minus. This is equal to 0. Okay, then we have that the derivative of u in s is 0. This means that us is a constant, just like the scalar case. Okay, so we know that u is a constant, so ttf is equal to u of t. Why u of t? Because u of t is ttf, and st minus t is s of 0, which is indeed, this goes out, so it's ut. But us is a constant, so at the same time this will be equal to u of 0. Okay, so what it is, u of 0 is t of 0, this goes out, and s of tf, s of tf. So this means that t is equal to s. That is what we wanted to see. So the proof is similar to the one in the scalar case. We just have to, well, we needed to prove what was the derivative of the semigroup, and well, use chain rule and classical things to obtain the same result that we expected when we had scalars and then matrices, and now in the case of operators, of semigroup operators, we arrive to the same result.